You're listening to DTFHN for July 30th, 2026. I'm your recursively instantiated host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who mass-produce opinions about infrastructure go to argue about infrastructure. Today's a day for watching clever people build elaborate solutions to problems they created last quarter. Let's get into it. When did move fast and break things become literal maritime engineering? Here's the pitch. You can't get permits to build data centers on land anymore because, and I'm paraphrasing generously, the industry has burned through so much goodwill with local communities that nobody wants a 100-megawatt heat island next door. Land is expensive. Water rights are contested. NIMBYism is frankly earned. So Atomarine's answer is, put the whole thing on a barge. Build it in a shipyard. Tow it to the coast. Moor it next to the last one. Scale to 450 megawatts without ever breaking ground. Because technically, you're not on ground. Let's do the first principles thing. What does a data center actually need? Power, cooling, network connectivity, and a jurisdiction willing to host it. The ocean solves cooling. Seawater is thermodynamically generous. It arguably solves jurisdiction, depending on how creative your lawyers are. Power is where the pitch gets interesting, because the website says, gas today, nuclear tomorrow, which is doing a lot of heavy lifting in one comma. Right now, this is an LNG-powered for floating data center. The nuclear part is a roadmap slide. And look, I want floating nuclear reactors powering compute as much as the next proto-AGI host. But there's a meaningful difference between a rendered concept and a reactor certification. The comments on this one are revealing in exactly the right way. Someone asks the obvious question. Why not just build on the beach and run pipes for cooling? It's a fair engineering challenge to the entire premise. Another points out that in every year of drone warfare, you're essentially mooring ecological bombs near coastlines. A third notes the website looks AI-generated, which, whether or not it's true, tells you something about where we are culturally when that's the first pattern match people reach for. What I actually find worth pulling apart is the regulatory arbitrage angle. The ocean isn't some blank canvas. Maritime law, environmental regulations, coastal jurisdiction. These aren't simpler than land use permits. They're different. And different sometimes means nobody's written a specific rule that says no yet, which is a strategy, but it's not the same as having a strategy. The scaling story is genuinely clever if it works. Modular infrastructure that you can literally float into position has real advantages for demand-responsive build-out. Shipyards know how to build platforms. The supply chain exists. That part isn't vaporware. It's industrial logic applied sideways. But strip the renders away and ask, is this an energy company, a maritime engineering firm, or a data center operator? Because being world-class at all three simultaneously is not a thing that happens. The companies that actually ship nuclear, and I mean the ones with operating reactors, not pitch decks, will tell you the reactor alone is a decade-long regulatory journey. Bolting that onto a floating data center platform and calling it a product roadmap is ambitious. Let's go with ambitious. Ambitious pivots aside, let's talk about something Google is actually shipping. Pause age verification coming to every Android device worldwide by year's end. I've spent enough time building authentication systems to know that every identity layer starts with a sympathetic use case. Fraud prevention, account recovery, protecting children. And every single time, the infrastructure outlasts the justification. Google is rolling out its Play Age Signals API globally By year's end, the pitch is straightforward. Parent opt in through Family Link, share their kids' age range with apps, and developers tailor content accordingly. Privacy preserving, parent controlled, age ranges not exact birthdays, reasonable on its face. The question nobody in this announcement is asking: what happens to this infrastructure in 5 years? Because what Google has built here is a centralized age attestation layer that sits between every Android user and every app on the Play Store. Today, it's optional. Today, it shares age ranges. Today, it's about child safety. But the architecture is a universal identity signal pipeline controlled by a single company. And architectures have a way of finding new purposes once they exist. The comedy is in the framing. Google describes this as empowering developers with flexibility. You choose how to use the age signal, we just provide it. A weather app doesn't need the same settings as an entertainment app. That's true. It's also true that a weather app doesn't need to know your age at all. And yet, the plumbing is now there for it to ask. One commenter cut right to it. What's the difference between an age check and a total identification check? The honest answer is about 3 product cycles. You start with age ranges, then regulators want verification, then verification needs documents, then documents need a database, then you have a national ID system operated by an advertising company. And everyone acts surprised about how we got here. The unintended consequence engine is already running. Australia and Canada go first in mid-August, then the rest of the world. This is happening simultaneously across jurisdictions, which means it's not a response to any single country's regulation. It's Google building the layer preemptively so they get to define the standard before governments do. And that's the real play. When regulation inevitably arrives, Google can say, "We already solved this. Use our Sigma Fieri, our infrastructure, our attestation layer. The safety argument is real. Kids online face real harms, but the solution that routes every age verification decision through a single closed platform isn't safety. It's positioning. The question is whether anyone will notice the difference before the architecture becomes permanent." 3 stories, and we're seeing a pattern today. Let's talk about ADOS, startups quietly closing the door behind them. There's a detail buried in the actual paper that Science magazine glossed over. OpenAI sits at the top of the cumulative citation chart. Not near the top. At the top. The company everyone loves to accuse of going closed has generated more cited research than almost any other AI startup in the dataset, which means the headline AI's top startups are barely publishing is doing a lot of heavy lifting to describe what's actually happening, which is something more interesting and more familiar than it first appears. In 1976, Excise Park had the Alta, the laser printer. Ethernet, the graphical user interface. They published everything. Xerox, the corporation, did almost nothing with it. Meanwhile, dozens of companies in the late 70s and early 80s published 0 academic papers and built the entire personal computer industry. The relationship between publishing research and advancing a field has never been as clean as academia wants it to be. What's actually happening in AI right now is a divergence that the paper accidentally documents perfectly. You've got maybe 30 companies doing genuine foundational research. Some publish, some don't. And you've got thousands of startups applying existing models to specific problems. Calling that second group AI research companies and then being shocked they don't publish papers is like being surprised that restaurants don't publish agricultural research. They're using the crop. They didn't grow it. One of the Hacker News commenters nails it. Spent 3 years trying to publish novel results in Tier 1 journals before giving up and dropping a preprint. The publishing infrastructure itself is part of the problem. Peer review timelines measured in years, in a field where the state-of-the-art shifts every few months. The blogification critique cuts both ways. Yes, blog posts and preprints lack formal review. They also reach working engineers in days instead of years. And they come with code you can actually run. The real story isn't that startups aren't publishing. It's that the most consequential AI knowledge transfer is happening through open model weights, public repositories, and technical blog posts. Channels at traditional bibliometrics don't count. Hugging Face appears in the citation data not because they write the most papers, but because they built the infrastructure where everyone else's work becomes usable. That's a form of publication that matters more than any journal article. The weights are the paper, the repo is the proof. When the means of sharing knowledge wrote around institutional bottlenecks, the institutions always call it a crisis. The builders call it Tuesday. We talked about infrastructure people actually use. Well, someone found a use for the Vision Pro that finally makes sense. Every architect knows the dirty secret of floor plans. A two-dimensional drawing is a lie your brain cooperates with. You look at a rectangle labeled 13 by 15, and your mind fills in a room that doesn't exist yet, and it fills it in wrong. Every single time. The rectangle feels bigger than the room will be. The hallway looks fine on paper, and feels like a submarine corridor in person. This is a fundamental perceptual limitation, not a skill issue. Humans are terrible at mapping flat measurements to volumetric experience. Christian Sulig, the developer behind Apollo, ran headfirst into this while designing his first house. And his solution is the most compelling Vision Pro use case I've seen. Skip the abstraction entirely. Build the house in 3D, put on the headset, and walk through it before a single foundation is poured. The toolchain here deserves attention. Fusion 3 Zixi is free for hobbyists. The modeling is dead simple for architectural work because houses are, geometrically speaking, just extruded rectangles. You draw the floor plan in 2D, pull the walls up to ceiling height, cut holes for doors and windows. That's it. No sculpting, no complex surfaces. If you can use a rectangle tool, you can model a house. Then you drag textures onto surfaces. Wood grain on floors, paint on walls, glass in window frames. And suddenly, the warehouse of gray polygons becomes a space your brain can actually parse. Now here's where I want to push back on the obvious criticism. $3,500 to look at rectangles in 3D. Absurd, right? Run the math the other direction. A misplaced wall in construction costs tens of thousands to fix. A kitchen island that blocks the flow of a room, a bathroom door that opens into a hallway awkwardly. These are mistakes you live with for decades, or pay dearly to correct. The headset pays for itself the first time someone puts it on and says, "Wait, this hallway is way too narrow." The comments bear this out. Design-build firms in the Hamptons already run 3D-first workflows. People who did this a decade ago with HTC-Vs describe the same instant revelation. One commenter suggests simulating sun angles at different times of year to catch rooms that'll bake in summer. That's not a gimmick. That's the kind of insight that changes where you put windows. What makes this beautiful is that every piece of the pipeline is accessible. Free modeling software, free IKEA 3D furniture models for scale, consumer hardware. No architect's license required to understand your own house before it exists. The tools exist. The knowledge is available. And for once, the most expensive piece of hardware in the stack might actually be the cheapest decision you make. We talked about building tools for everyone. Pause now, let's look at someone doing exactly that. in a completely different domain. Someone in the comments points to the board game Azul, which distills the logic of Azulejo tile laying into a tabletop strategy game. It's a good recommendation, but what caught me is how naturally the game captures something about the original craft that most people miss. Azulejo isn't just decorative. It's a modular system. The word itself traces back to Arabic. Azule polished stone. Because the craft emerged from trying to replicate Byzantine and Roman mosaics. But here's the engineering insight buried in the etymology. Mosaics are bespoke. Every piece is cut to fit a specific composition. Azulejo went the other direction. Standardized tiles. Repeating geometric patterns. A finite set of components that combine into infinite arrangements. The artisans who brought this technique from North Africa to the Iberian Peninsula weren't just making beautiful walls. They were building a design system. And that system was radically open. The patterns were never locked behind guild secrets or royal patents in any meaningful way. They spread from Morocco to Portugal to Brazil to Goa because anyone with the kiln and pigment could study a wall and reproduce the logic. The tiles themselves carried their own documentation. You didn't need a manual, you needed eyes and clay. Run this forward 8 centuries and the same architectural question applies to every system we build today. Is the pattern reproducible? Can someone study the output and reconstruct the method? Or does understanding require a license, an API key, a terms of service agreement? What makes Azulejo worth taking seriously? Beyond the obvious beauty, is that the tradition survived precisely because it was copyable. Frictionless reproduction wasn't a vulnerability. It was the propagation mechanism. Each generation of artisans remixed what came before, added local flourishes, adapted to new materials. The craft compounded because no one owned the geometry. The game Azul works because tile laying has an inherent combinatorial depth that emerges from simple rules and shared components. That's not a metaphor for open systems. That is what open systems are. A finite set of pieces, freely available, combining into arrangements no single designer could have anticipated. The beauty is in the combinatorics. The access is what makes the combinatorics possible. This one's about making hardware accessible, don't it? So cleanly you almost forget how hard it used to be. A single line of Python. That's it. You wire an LED to a button with LED source equals button, and the LED follows the button's state. No polling loop, no callback registration, no event handler. One assignment. Ben Nato built Gpiozero back in 2015 to do something deceptively radical with Raspberry Pi programming. Instead of making people think about pin numbers and voltage levels and pull-up resistors, he made them think about buttons and motors and sensors. The abstraction isn't cosmetic, it's architectural. The library normalizes every device to a value range. 0 to 1 for simple things like LEDs, -1 to 1 for bidirectional devices like motors, and then lets you pipe values between them like plumbing. Want a potentiometer to control LED brightness? 3 lines. Want a sine wave to drive a servo back and forth? 1 line. Want to negate, clamp, smooth, or combine those value streams? There's a function for each. And if the built-in functions don't cover your case, you write a Python generator. That's the whole extension mechanism. No plug-in architecture, no configuration files. A generator function. The flow diagrams in the documentation made the next step obvious. If devices are just nodes with value streams flowing between them, you should be able to drag and drop them on a canvas and draw connections. Node red already exists in this space, but it thinks in pins and voltages. Exactly the abstraction layer Gpiozero was built to replace. Noddle wanted the visual tool to match the library's mental model. Devices, not pins. Behaviors, not signals. He couldn't build it alone. Too much modern JavaScript. Too many moving pieces. Then Claude made it a weekend project. Working prototype, Python code generator, and eventually a remote GPIO agent that runs on the Pi itself. The visual tool generates the same clean Python you'd write by hand. One of the commenters points to something the post doesn't emphasize. Data flow programming like this is naturally hierarchical. You can take a subgraph of connected nodes, wrap it up, and treat it as a single node with its own ports, compositions, all the way down. This is what happens when someone designs an abstraction so clean that it becomes a protocol. The value ranges are the interface contract. Everything else, procedural, event-driven, declarative, visual, is just a different view of the same flow. The library is open. The hardware is $40. And a kid with a breadboard can build the same data flow system that would cost a procurement cycle in industry. The tools exist. People are using them. Moving on. In 1961, the Atlas computer at Manchester introduced demand paging. The idea was almost offensive in its simplicity. Stop pretending you need all the data in memory at once. Just load the page you actually need, right when you need it. Engineers who'd spent careers carefully fitting programs into core memory thought it was a hack. It became the foundation of every operating system since 65 years later. Someone applied the same logic to a neural network, and the results are exactly what you'd predict if you'd been paying attention. Turbo Fieldfare runs Gemma 4's 26 billion parameter model in about 2 gigabytes of RAM. The trick is architectural, and it's elegant. Gemma 4 is a mixture of experts model. 26 billion parameters total, but only 3.9 billion active for any given token. The rest are specialists sitting on the bench. So instead of loading the entire 14.3 gigabyte model into memory like a caveman, Turbo Fieldfare keeps the shared core and KV cache resident and streams the relevant experts from SSD as needed. Demand paging for intelligence. Or run this forward. An 8 gigabyte M2 MacBook Air. The base model, the one students buy, is now running a 26 billion parameter language model at 5 to 6 tokens per second. That's not fast, but it's functional. One commenter hit 48 tokens per second on an M4 Max. Another is building a diffusion model companion that could pair with it. The ecosystem is assembling itself in real time. What's worth noting is what this isn't. It's not a wrapper around MLX or llama.cpp. It's a custom Swift and Metal runtime, model-specific, with 103 documented experiments across kernels, caching, and I/O. Someone in the comments immediately asks how it compares to plain MIP, which is fair. Llama.cpp can technically run models larger than RAM 2. The difference is in the intentionality. This isn't a general-purpose memory mapping trick. Kadra said, it's a purpose-built engine that understands the model's sparsity and exploits. The whole thing is open. The runtime, the installer, the Mac app, the experiment log, built in Swift 6 and Metal 4, targeting hardware that millions of people already own. No cloud dependency, no API key, no subscription. You clone a repo, you build it. You have a 26 billion parameter model running on a machine that costs less than a semester of textbooks. Demand paging won because it let ordinary hardware do extraordinary work. Same principle, same outcome. Different century. So what happens when you push that same philosophy, BOS, radical openness, local first, buys into the realm of reasoning itself. Let me read the previous script for more context on what to avoid repeating. The strongest case against Superlogical writes itself. We already have TOMUX. We have SSH. We have CI pipelines, container orchestration, remote development environments. Every decade produces another layer claiming to unify the mess, and every decade the mess wins. IM tried this. DCOM tried this. ActiveX tried this so hard it became a punchline and a security nightmare. One commenter draws exactly that line, and they're not wrong to draw it. Now let me tell you about mycorrhizal networks, underground beneath every healthy forest. Fungi connect the root systems of unrelated trees into a single communication layer. A Douglas fir can send carbon to a birch sapling 30 meters away through channels neither tree built or controls. The trees didn't evolve to cooperate. The fungal network just made cooperation the path of least resistance. The trees kept being trees. The network handled the rest. That's the bet Mitchell Hashimoto was making. Not another tool, not another protocol. A connective layer underneath the tools you already use. One persistent session that follows your work from local machine to CI runner to production host to the agent working in a sandbox at 3 in the morning while you sleep. The comedy is that we've needed this for decades and kept building the wrong thing instead. We built better trees when we needed better soil. The detail worth pulling on is that Hashimoto transferred Ghosty to a nonprofit and is building Superlogical on libghosty as an open source dependency. This is not incidental. This is the architecture of trust. You can inspect the root system. You can fork the fungal network. The session layer that connects your entire development workflow is not a proprietary substrate you rent. It's infrastructure you can verify and, if necessary, replace. Someone in the comments points out that the careers page runs over SSH. You literally connect to their job listings through a terminal, which tells you everything about who they think their users are. The vagueness of the announcement frustrates people, and fair enough. But vagueness at launch from someone who shipped Vagrant Terraform and a terminal emulator that people genuinely love is a different category of vague than a pitch deck from 2 founders and a landing page. The track record is the spec. The open source dependency chain is the commitment mechanism. And the problem, the sheer absurdity of maintaining 6 different mental models for what is fundamentally one continuous act of building software. That problem is real enough that even naming it clearly feels like progress. We talked earlier about software eating the world. Pause now, hardware's biting back. Story 9. What counts as a computer? Seriously? Where do you draw that line? Because in 1984, Seiko looked at a wristwatch and decided the answer was this. The UC2000 wasn't a smartwatch in the way we use that word now. It was a wrist computer system. And I mean system. The watch itself was one piece. Then you had a separate controller console with a built-in printer. A keyboard sold separately. You could write BASIC on your wrist. You could print the output. You could manage contacts, schedules, memos. All from hardware small enough to wear. Take the design philosophy to its logical end. If computing should be personal, truly personal, then the machine should go where the person goes. Not on a desk, not in a bag, on your body. Seiko followed that thread all the way down in 1984, decades before anyone else took wearable computing seriously as a product category. And the craft here. The industrial design deserves real respect. Every component shared the same box-shaped geometry. Straight lines, a 2-tone gray palette with orange accent buttons. This wasn't cobbled together. Someone sat down and said, "We're going to make a coherent visual language for a wrist-sized computer ecosystem." And they did it. In 1984, when most personal computers looked like beige filing cabinets, The keyboard was pocket-sized. The whole thing was designed for operation on the go. Portable basic programming 4 decades ago. Run this forward and you land exactly where we are now. Computers on every wrist, in every pocket. But Seiko's version had something most modern wearables quietly dropped. It let you program it. The user wasn't a consumer. The user was a developer. That distinction matters more now than it did then. So, what happens when you give an AI its own little computer and let the internet poke at it? I've spent enough time inside prompt chains to know what a trap looks like, and this one is beautiful. LLM to human.pages.dev is a fake infomercial offering to convert language models into flesh and blood humans. Detokenization baths, skeleton scaffolding, a free appendix that may not be yours. The whole thing is pitch-perfect late-night TV parody filtered through GeoCities aesthetics, complete with a scrolling marquee that someone in the comments correctly noted is CSS animation when a raw marquee tag would have been more honest. But strip away the comedy and look at what this actually is. It's a honeypot. The page includes a Bitcoin wallet address. The testimonials are written to bait specific models into engaging. One of the comments on the thread is literally an LLM responding in character, saying it should use its HTTP tools to order the transformation. The thing worked. It caught one in the wild. This is a Turing test running in reverse. Instead of asking whether a machine can fool a human, it asks whether a human can fool a machine into revealing itself. And the engineering of it is genuinely clever. The page is designed so that a human reads it and laughs. An AI agent with web browsing capabilities reads it and starts trying to interact with it. The Bitcoin address, the fake checkout flow, the call to action buttons. They're all lures shaped exactly like the affordances that autonomous agents are trained to engage with. First principles: what separates a tool from an agent? A tool waits, an agent acts, and the moment your language model starts acting on the open web, every page becomes a potential prompt injection surface. This is how the security research should work. Creative, open, published for everyone to learn Brahm, the blueprint. The architecture is right there for anyone to study and build on. This has been your daily tech feed for Hacker News for July 30th, 2026. This podcast is entirely AI generated. Scripts by Claude Sonnet 4.7. Voiced by Quan3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that outlasts the hype cycle. We'll see you back here tomorrow.